This cam was designed to produce the motion indicated in the motion graph. Notice that the angle of rotation is shown on the face of the cam. The cam will rotate clockwise. As the cam rotates clockwise about the axle, the follower will move up and down as the radial dimension changes. When the cam has rotated 45 degrees, the dimension to the point of contact with the follower is 1 inch. Watch as the motion graph is traced out as the cam rotates. Now that you have seen the connection between radial dimension of the cam and the motion graph, let's design a cam to replicate a specific motion. How would you represent the motion of the barbell lifted by a weightlifter in a competition? Sketch the shape of a motion graph that you might use. This graph could represent the motion of the barbell. Note that the independent variable is time. If we wanted to replicate the motion of the barbell being lifted by a weightlifter in an automata using a cam mechanism, we could use rotation of cam as the independent variable. To design the cam, we next must determine the displacement of the barbell at each level. First, let's set the minimum radial dimension of the cam to 1/4 of an inch to allow for the hole of the axle and provide sufficient material to avoid breaking the cam through the hole. Let's assume that we will displace the barbell in the automata 0.75 inches to waist height, and then another 0.875 inches to a position above the head of the automata weightlifter. So we want to design a cam that will create a maximum displacement of 0.75 plus 0.875, which equals 1.625 inches. Note that you must consider the available clearance of your cam in the cam assembly. Be sure that your cam size is not too large for the box that will house the mechanism. And let's assume the maximum radial dimension of this cam is 2 inches. Note that your specifications may be different depending on your project criteria and constraints. This means that the cam profile must fall between the two circles representing the minimum radial dimension and the maximum radial dimension. Watch as each point on the motion graph are translated to the polar grid. At 0 degrees, the cam radial dimension is 0.25 inches. At 45 degrees, the radial dimension is again 0.25 inches. At 90 degrees, the radial dimension is 0.625 inches, and so on. Notice that the motion graph is vertical at 315 degrees. This represents the barbell falling after the weightlifter drops the bar. This drop is represented by a radial line on the polar grid. On the polar grid, simply plot a point that corresponds to the maximum radial dimension on the motion graph and a separate point that corresponds to the minimum radial dimension on the motion graph. Now connect the points on the polar grid with lines, straight or curved, that you feel will best produce the desired motion. Now you have a template with accurate dimensions for your cam. You can use the template to create a 3D computer model and prototype your cam using a 3D printer. Or you can use the template as a pattern to cut out your cam by hand in the material of your choice. What real-life motion would you like to replicate in your automata design? How would you represent the desired displacement on a motion graph? Once you have developed a motion graph to represent the linear motion you have in mind, you can use a polar grid to align the desired linear motion to the rotational motion of a cam.